I have time, about two topics which seem to be formally not related, but effectively they are very deeply related, as you will see during my talk. And effectively, the relation between them indicate to very big problems in our understanding of fundamental theoretical physics. So let me start from the first topic, which is related with the study of modified gravity. So first of all, I will give some introduction. So many of people, and I guess many of people who are still there, they assume that the only correct gravitational theory is general relativity, Einstein gravity. Unfortunately, it's not so. It's not correct theory. It's just approximate description of gravitational forces in our universe. And the reason is very simple. When we start to calculate quantum effects in curved space-time, we will induce some terms which are high derivative terms in curvatures. So even if you consider that your quantum gravity, and we believe that gravity as other fields is also quantum object. So if we believe that general relativity is quantum gravity, and we do any calculation at the early universe with general relativity, we have modification of general relativity due to these high derivative terms. They're just induced when you do one loop corrections. That is more or less the same what happens in usual quantum electrodynamics. If you study quantum electrodynamics using textbooks and you do corrections, I mean, you do one loop calculation or multi-loop calculation, you will come to kind of Euler-Heisenberg electrodynamics, which is just Maxwell electrodynamics with high derivative terms. So then there appears that such terms, so gravitational terms which differ from usual curvature, they are very important, especially at early universe where curvatures are very strong. Another interesting property of gravitational theory is that early time inflation may be described by just gravitational theory. Of course, we know that there are many possibilities. We believe to this paradigm that early time inflation is some specific property of early time universe. And during last 40 years, we actually have on the market, I don't know, I would say several hundred different inflationary models, which describe inflation very well. Most of them, because we have still very low observational limits. Sorry. Just I will down. So we have just a couple observational indication for inflation. So many of models may pass easily inflation, and then of course gravitational theory may also pass inflation successfully. And unlike to usual inflation, which is described by some scalar field, that is most simple and most common theory for inflation, there is no problem with gravity in this respect, because when we take scalar field for inflation to describe inflation, we should explain after all how the scalar field disappears after the inflation era. And then if we continue to think about scalar field for dark energy, again, the question is how this scalar field may reappear in the dark energy and why it was invisible during these two periods of accelerating universe. Moreover, in the study of universe evolution, it's quite possible within modified gravity theory, actually within different classes of modified gravity theory, to give unified description for the whole universe picture, universe history picture. So starting from inflation and up to dark energy. Even more, we can do it starting from inflation, including radiation and meta-dominant era and dark energy, just within same gravitational theory. Of course, it looks very attractive because we know that gravity exists. In this case, we even do not insist on its quantum nature, because we can do description just within some specific gravity theory, which is considered to be classical. So quantum effects we may neglect. We may take it after all, after we have the description of modified gravity, I mean, quantum gravity available. So that are the reasons why modification of general relativity, for instance, FR gravity, is so attractive, because we can give the description of the whole universe evolution. If you look now to the current papers, theoretical papers, I mean, not observational papers, you will see that mainly they're concentrated only to one epoch. So one paper describes inflation and says nothing about dark epoch. Another paper describes, I don't know, meta-dominance, but then there is no way from this theory how to get dark energy era or inflation inconsistent. Now, it's also interesting that from modified gravity, we may also get dark matter. So it's extra benefit, but it's interesting. If you look to particle models of dark matter, we currently have, I don't know, I mean, it changed very often, but we currently have from 30 to 40 dark matter candidates, and people who work within these models, they claim that only his model is consistent model and realistic model. For me, most interesting and most attractive and probably most realistic model is axion dark model, and I will talk about this dark model today. But as I told, dark matter model. As I told, dark matter model may be obtained also from modified gravity, and that is quite interesting possibility. In fact, we have now many proposals for modified gravity, because we have the universe evolution, and we want to understand by which theory it may be described. So maybe it may be described by general relativity with scalar field, or it may be described by some modified gravity. So there were many attempts, and there are many different theories on the market. Most developed and most attractive theory is so-called FR gravity, where instead of general relativity, we have some model with function of the curvature. Okay, such model may be considered as kind of dynamical cosmological constant, and this model is attractive because it has no ghost, so that is ghost-free theory. And then, as ghost-free theory, it does lead to some inconsistencies which other alternative gravities may have. Another interesting model is so-called modified Gauss-Bonnet gravity. In this case, we add to usual curvature invariant, we add some function, which is function of Gauss-Bonnet invariant. And due to fact that Gauss-Bonnet invariant is topological invariant in 4 dimensions, but it's not topological invariant as function of Gauss-Bonnet. So due to this property, we have significant simplification of field equation. I have to mention that unlike to general relativity, field equations in modified gravity, they are high order field equations. And our usual physics, it's physics of harmonic oscillator. So it's physics with two derivatives. And here we have 4 derivatives normally, sometimes more. We have some approaches related with non-local gravities. So non-local gravities where curvature invariants appear in the denominator of our term, of our action. And this series also may be interesting for description of the inflation and dark energy epoch. However, they are much more complicated than, for example, FR gravity, so it's more hard to work with them. From string efforts, so from string theory, which is currently somehow declining because many string people who study string theory during the last 40 years, they moved to cosmology or some related condensed matter physics. So from string theory, we also have alternative gravity theories. Such alternative gravity theories basically they suggest not only high derivative terms, but they suggest also scalars. First of all, dilaton, maybe also other scalars from string theory spectrum. And it's interesting that string-inspired gravity is also ghost-free theory, and it may be used also for description of universe evolution. There is interest to Born-Infeld gravity, but Born-Infeld gravity is extremely non-local theory. It's somehow a generalization of Born-Infeld electrodynamics, where instead of usual term related with stress of electromagnetic field, we have Ricci tensor. But this theory is complicated, and even equations of motion are hard to get in this theory. So that is the reason why this theory does not attract so much attention now. There are more modified gravity. I can mention some of them. For example, there is so-called FT gravity, where we have under the action. So in the Lagrangian, we have function which depend on the curvature and stress energy tensor trace, okay, or even stress energy tensor quadratic. And again, such theories may be considered as modification of gravity theory, and they may give us some interesting information. What basic feature we may get from the list of such modified gravity theories? The story is the following. In general relativity, we have only curvature. Okay, so just we have the theory where everything is defined. Here we have the series. All of these are theories which have some functions of curvature. So using this functional form of the curvatures, we may play with equations of motion in such a way that we may get necessary background dynamics, which will be consistent with observational bounds as much as possible. Okay, so that is quite attractive property of modified gravity. I have to mention that there is also recently approach to modified gravity related more with mathematical physics, that is teleparallel gravity, where we consider affine connection not to be symmetric but anti-symmetric. We also non-metric gravity, where we consider that covariant derivative of metric tensor is proportional to some vector. So there are such attempts, but still these attempts, they do not bring us to more or less a realistic picture of the universe as we have with this modified gravity based on just metric description. Also, it's interesting that with modified gravity theory, we have a number of interesting properties which we thought may not happen or may happen only for very specific theory. For example, local solar tests. In textbooks on general relativity, we learn for many years that the only one gravity theory which pass local solar test, so test of solar system, is general relativity. However, now we know that among all of these theories, there are huge classes of the theory which easily pass local solar test, so observational test of solar system. That means that if we are within solar system, basically we don't see big difference between, at least on observational level, we don't see the difference between general relativity and such theory. Of course, going deeply, for example, going to the study of gravitational waves, we probably can find some difference, because gravitational waves from general relativity, they are different from gravitational waves of any of such theories where we have extra polarizations. So if we find observational indication to extra polarization, we may say that even in solar system, we have, for example, some theory which is more preferable as realistic theory than general relativity. So far, no. And it's also interesting that with modified gravity theory, we have number of novel physical phenomena. For example, stellar astrophysics. We have here many specialists, very deep specialists in the study of neutron stars and related astrophysics. And there are some questions which are known for this specialist, but somehow they are not on very wide discussion. So if we consider, say, stellar astrophysics in frame of modified gravity theory, we can try to solve these theoretical problems in stellar astrophysics. For example, we can using Tolman-Oppenheim Volkov approach, so standard approach in general relativity to stars, we can get corrections thanks to modified gravity, and as a result, we have somehow different description. So we have corrected description of stars, neutron stars, even white dwarfs, where gravity may help us to solve some problem. For example, to realize neutron stars with large radius of about 10 kilometers. Also, we have the possibility to realize wormholes in modified gravity in easy way. We also have very interesting novel black hole description in modified gravity, because thanks to high derivative terms, we may have even entropy to be negative when we study black holes in such theories. So we have plenty of different phenomena, and that is the study. So now I start with a specific model. So let me present you the model where we can unify all known dark components of the universe within simple, quite simple theory, which is realistic and which realistically explains the universe history. So the Lagrangian or action of such theory is the following. Instead of usual curvature term, we have here some function of curvature. We have here non-minimal coupling of scalar term with some function, another function of curvature. And we have here kinetic term and potential term for scalar. That will be the theory by which we want to describe the whole universe evolution. Of course, without taking into account very small effects. So for notations, we use here gravitational sector. So that will be a gravitational sector, and that gravitational sector includes some function of curvature plus non-minimal coupling of scalar with curvature. We have equations of motion. If you look to these equations of motion, you immediately see that these equations of motion are of higher order, because we have, for example, here some function of curvature, and if curvature is, for example, a square, so curvature squared, we will have 4 derivatives. Already from here, we see that we have 4 derivatives in this equation. And also, we have scalar field equation. The reason why I try to show here how to unify the inflation with dark epoch and with realistic dark matter is, as I think, very soon we will have some news about which dark matter is most realistic candidate. So there are indications that that is axion dark matter. So I will try here to explain the universe evolution, including all 3 dark components of the universe, taking the scalar field as axion dark matter. So for FR gravity, we select just A square gravity. It's not necessary, but A square gravity is quite simple theory. And with such theory, we know that we have excellent inflation, which is consistent with observational bound. Okay. Then we have this non-minimal term. And for non-minimal term, we should take the following choice, so that this non-minimal coupling of axion field with modified gravity would not spoil our inflationary epoch. So we should put some restrictions to this term so that it would be invisible during inflation, or would give some very small contribution. So to do this, we propose that this function is inverse proportional to the scalar field with some parameter. Power, this parameter is positive. And also this function g, which is multiplied to function of scalar, has also power law form with parameter gamma, which lies between these 2 fields. Now, let's go to unified description of inflation and dark energy in the presence of axion field. So, in all this story, we consider that axion field is slowly, it gives slowly varying reheating. So there is no much to say here. In principle, the study of axion field is quite well developed. So there is very big literature, including observational bounds, including different theoretical models. The axion theory I'm talking here is based on so-called misalignment model, where we have primordially broken U1 Pichet queen like symmetry. Okay. So the details of that are not really important for us. As I told, they are known in the literature. Here, I just want to show how it may be used for unification of dark matter with inflation and dark energy. Okay. So we put the following restriction to the potential and non-minimal and gravitational term, so that non-minimal coupling would not influence inflationary epoch. So that is the main point. So we want that inflation would be given by A square gravity only, and non-minimal term would not influence it, or if it influences, it would give only next to leading order correction. Okay. So then this condition is imposed. So with this condition, we know that this non-minimal term doesn't influence inflationary epoch, and then we should check that this non-minimal term also does influence the preheating stage, so after inflation. So during the inflationary era, the mass of axion is constant, and then axion fields acts effectively as effective cosmological constant only. So it changed a little bit inflation, but it does it changed only in quantitative way. So selecting the corresponding coefficient of R² term, this influence is negligible. For cosmic times, when Hubble parameter is bigger than axion mass, we consider the potential for axion field, which is just massive term, and we work with this axion, which is somehow funny rewritten in terms of so-called axion decay constant and initial misalignment angle. So we can say several words about axion field dynamics. So scalar field dynamics, or axion field dynamics, as massive term is just oscillating after inflation, is standard scalar field. As I told, because of our restriction to non-minimal term, there is no influence here of non-minimal coupling of axion field with scalar. And we seek such oscillating solution for scalar field. So going through some simple mathematics, which is textbooks mathematics. So we work with this equation, we substitute this proposed solution, and we solve it, and we come to the solution for this function and for axion energy density in the following form. Okay, so we see that energy density of axion, which is given here at leading order, is just standard dark matter energy density. So in such a model, we achieve that we have consistent and realistic inflation, which is given by R² gravity. And on the same time, we have axion, which is embedded in this model, which gives quite nice preheating error after inflation. Now, the point is how we may connect all this picture with dark energy epoch. Okay, so let's continue with background evolution after inflationary era to first just on the level of equation to show that zeta equations of motion. Non-minimal coupling is negligible, and this equation of motion for R² gravity gives us standard R² inflation, which is quasi-de Sitter inflation with excellent correspondence of the calculated parameters of such theory with spectral index of primordial curvature perturbation and tensor to scalar ratio in the region where we have such bounds. So now we go to dark energy epoch. Okay, for dark energy epoch, we use the fact that axion field will start oscillating more and more, approach to dark energy, because immediately after inflationary era, when Hubble rate is proportional to axion mass, we have this oscillation. So we should study Friedman equation, Friedman-Robertson-Walker equation, and to say something about the role of axion in dark energy epoch. So we write equations of motion. Okay, we write equation of motion, and we see that in these equations of motion, if we look to these equations of motion carefully, this term is important only at inflationary epoch. This term also is important at inflationary epoch. Terms related with axion, they're important at preheating era. So the leading terms remain these non-minimal coupling terms because of our restriction. Indeed, for example, this term, it contains the power of curvature, which is negative. So this power is negative. And as a result, at dark energy epoch, curvature is extremely small. So being negative in negative power, this term is rather big. The same for this term. Okay, so we come to approximate Friedmann-Robinson-Walker equations of motion, which gives only relation between non-minimal term effectively. Okay, so we can solve it. We can find a Hubble rate parameter for such theory. So it's nearly de Sitter. So if we approximately solve this equation, we got Hubble rate, which is approximately constant. So we have nearly de Sitter space. So we have late time evolution of the universe, which is de Sitter evolution. So we got in such description, we got very interesting result. So we have the theory where we get within the same theory description of inflation with dark matter. On the same time, non-minimal coupling of dark matter with curvature give us correct dark energy epoch. Of course, that was just example. We may go further. Okay, so we may, for example, consider other theories and use other forms of axion dynamics. For example, we may consider the theory, modified gravity theory, where we have more terms, so that this sector describes inflation, and this term are responsible for dark energy epoch. Okay, so we have these two terms for unification of inflation with dark energy, and axion field we use only for preheating and for description of dark matter in terms of axion. Again, in such way, we always we also can get unified description of the universe history. So the main story of all this, without going into detail, because I see that you are already a little bit boring, is the following: that within some theoretical model, which is gravity theory, which is modification of usual general relativity, we can describe the universe history as a whole from the very beginning, I mean, after Big Bang, because we don't know what was Big Bang, what it caused, how were quantum gravity effects during it. So after Big Bang, inflation, radiation matter dominance, and dark epoch within the same theory. Moreover, in theory of that sort, we have excellent agreement with, for example, with observational bounds, for example, Planck for inflation. And we also have up to the same accuracy as usual lambda CDM model. We have also very good results when we compare theoretical prediction from such model and observational bounds for dark energy epoch. Okay, so there is no big difference. The only some weak point which may be indicated is that one can say that, for example, to describe dark energy, we need the theory where there are more parameters. For example, here in this form, we have, you see, 1, 2 parameter and 1 parameter, which is coefficient of this term. We have 3 parameters. So one can say that, for example, maybe lambda CDM is more economical, what I doubt, but nevertheless. So,
the parameters of inflation. Here you have inflation for free.
Yeah.
In lambda parameter, you need all the parameters.
No, this you are right in the following sense. We have here two parameters, but this term is not essential for inflation. So with these 2 parameters, you play for dark energy. So now, in the rest time, I want to go to another subject, which is very much related with this subject. So, modified gravity, alternative gravity. In that theory, we have modification of Friedmann-Robertson-Walker universe equation. Okay, so our gravitational equations are different from general relativity. So we select different theories and we come to different gravitational equations, and these different gravitational equations may give us different universe evolution, which we should compare with observational bounds and say which is better. Now, very similar property is related to entropy, and I will talk now about this. So at university, most of you, and for example me, we have been studied that entropy is unique, universal, and fundamental quantity, okay, which plays the most important role in physics. So entropy is most important. Now, we have many different disciplines from quantum physics, quantum gravity, thermodynamics, information theory, etc., etc. Okay. So we see now that entropy, in fact, depends on physical system. And to describe entropy in specific physical system, we use different entropies. Especially difference appears when we study classical and quantum systems. So there are many different entropies, and which of these entropies, how they are related, why they appear in different way, why they are not fundamental as we thought from the golden days of classical thermodynamics. Okay, I will talk about entropy from the point of view of black hole. So, in theoretical physics in 70s, one of the most important discoveries was that black holes are not called objects, but they have entropy and temperature. Okay? So, in 70s, Bekenstein proposed that black holes, they may have entropy, and the entropy should be assigned to describe it. It was not considered as interesting proposal, so it was not very well accepted, and it was just considered as speculation. After that, Hawking, when he studied Schwarzschild black hole, and after that he extended it to other black hole, he found that black hole radiate quanta, and they emit black body spectrum with temperature of that formula, where m is black hole mass. Okay? So after that, that discovery of quantum radiation from black holes made sense of black hole entropy, because in that way we can indeed apply classical thermodynamics to black holes. So there were many after that there were many problems between Bekenstein and Hawking. I heard in one conference when each of them pretended to be that only he invented black hole entropy, but as we see, both of them, they made, in my impression, equal discovery. So the well-known property of Bekenstein-Hawking entropy is that it's not proportional to black hole volume, what we normally have in standard classical thermodynamics, but it's proportional to black hole horizon area. Okay, so we have in classical thermodynamics the entropy proportional to its mass and volume, and in black holes we have different way because it's proportional to surface horizon area. So related with this fact that entropy is strange for black holes, there appears some studies which try to apply different entropies for description of black hole thermodynamics. Okay, so let me just give you some example. So Bekenstein-Hawking entropy is given by the following formula, where we have area of the horizon, and we have here horizon radius. Okay, and that is the fundamental proposal for description of entropy in black hole. However, there are many other entropies. For example, there is so-called Tsallis entropy. It appears in non-extensive statistics for systems with long-range interactions. Okay, so totally different field, no relation with black hole. In this case, partition function diverges, and standard Boltzmann-Gibbs entropy is not applied anymore. So that is the, in terms of say black hole, we have the description of this Tsallis entropy as a follows. So we see that Bekenstein-Hawking entropy is recovered when we have this parameter equal to 1. Okay. Now we have another entropy. I try to list many, but eventually some of that entropy I even don't know. So we have Renyi entropy, okay, and that is index specifying the amount of information. So it's not even physics, it's information. Again, in this case, that is some function of Bekenstein-Hawking entropy, which has the limit to Bekenstein-Hawking, of course. We have so-called Sharma-Mittal entropy, which is again one more formula in terms of this Tsallis entropy, where these two parameters are phenomenological parameters, which should be defined by experimental data. Okay, we have so-called Barrow entropy, which may be considered as example of Tsallis non-extensive entropy, but it was proposed as the entropy to describe form. So it was proposed as the entropy to describe quantum gravity. So we have many different entropies, not only in physics, but also, as I said, in information theory, statistical system. Okay. So, for example, one more entropy for statistical system, that is this type of entropy. One more entropy for loop quantum gravity, which is related with non-extensive statistical mechanics, that is this entropy. And this entropic index here quantifies the probability of frequent events, okay, compared with unfrequent events. So all these entropies, they have following properties. Generalized third law. So all these entropies vanish when Bekenstein-Hawking entropy vanishes. Okay. So in usual third law of standard thermodynamics, we know that entropy vanishes when temperature vanishes. However, we know again that for black hole, Bekenstein-Hawking energy diverges when entropy vanishes, and it vanishes when temperature goes to infinity. So it has different properties. Now, all the above entropies are monotonically increasing functions of Bekenstein-Hawking entropy. All these entropies are positive in the same way as Bekenstein-Hawking entropy. Yes. And all this entropy reduced to Bekenstein-Hawking entropy. Then there appears natural question. Can we somehow connect all these entropies looking to really fundamental quantity, which gives a specific example, this entropy? And the answer is positive. So we may give the example of entropy. So that is example of entropy, which depends on 6 positive parameters. Okay, and this entropy satisfies to all above properties. So positivity, Bekenstein-Hawking limit, increasing monotonically increasing function, and generalized third law. Moreover, if look carefully to this entropy, we find that in the limits, in the corresponding limits, from this entropy, from this generalized entropy, we can get all the entropies we talk about. For example, for this theory, when we take these parameters as the following, we introduce this Tsallis entropy, etc., etc., etc. So one by one, we introduce all known entropies. So that indicates that in principle, we do not understand something with entropy, and some fundamental entropy is somehow hidden, because eventually that is not the only possibility. So somebody of you may invent another function which satisfy to above conditions and give in the limit all these known entropies. So that is of course true. Important question is the following. As I told, the PS recently attempts to apply all these different entropies to black hole thermodynamics. Okay, so people say that eventually Bekenstein-Hawking entropy is not the only one. Let's consider black hole with Renyi entropy within Renyi thermodynamics and calculate everything. Okay, so there is number of papers of that sort. And using this generalized entropy, we demonstrated explicitly that it's not correct, because if we do in such way, so if we use any entropy which is different from Bekenstein-Hawking entropy, then thermodynamics is broken. There is no temperature in accordance with Hawking radiation. Very simple, but interesting fact which was not found so far. Another, so I have
5 minutes.
Yeah, 5 minutes, so I'll try to be very quick, not to go to the data. So another, if we go further to the study of black hole thermodynamics using different entropy and using this generalized entropy, still we find some specific, usually multi-horizon black holes, where we see that, for example, under some conditions, generalized entropy could be still consistent with classical thermodynamics. But that is very specific, exceptional results. That means eventually, so we found several such examples. Nevertheless, the conclusion is the following, that it seems that despite to the fact that we don't understand what is fundamental entropy, and we don't know what is fundamental entropy, we have many different entropies, and we have generalized proposals for such entropy. The correct entropy in thermodynamics to describe black holes is only Bekenstein-Hawking. Another big circle of questions related with different entropy, and where these entropy studies are related with modified gravity, is so-called holographic dark energy models. So when we construct gravitational equations from thermodynamics, we may use thermodynamics law, and using thermodynamics law, we can arrive to general relativity, and we may arrive to gravitational equations. Now, very natural questions may be, okay, you did it from classical thermodynamics with classical entropy. Now, for example, you use this entropy, or you use Renyi entropy, or you use this Tsallis entropy, or whatever else entropy you use. So you also may restore from such thermodynamics gravitational equations, and these gravitational equations will be different from usual equations of Einstein gravity. Okay, so we have again variety of different modification of gravitational equations, and in that corner we have precisely connection with modified gravity, because modified gravity also gives you modification of gravitational equations, and from that corner you get modification of gravitational equations thanks to use of different entropy in thermodynamical description of gravity. And that shows that from one side it looks somehow as proposal, but nevertheless we may try to find the connection between the different fields of theoretical physics. That is, one is just entropy, because you understand that that is just function which is given ad hoc. So you can invent another function with 10 parameters, which has just the same properties. Nevertheless, we find that there are some connections. For example, correspondent modified gravitational equations may be reobtained from some modified gravity theory. And then there appears relation between alternative gravities and still yet not found fundamental entropy. Okay, so I try to show that there are some very interesting aspects of theoretical, fundamental theoretical physics in relation with gravity. And despite of many successes, we still do not understand some points which we thought we really studied already at second year of the university when we studied thermodynamics. So let me stop on this.
So now we have 5 minutes for questions, if there's any, the public, or from the Zoom as well. And next day, can you hear me? Ah.
No, in the first part, when you say this axion matrix, so what do you mean by axion matrix? So where this comes from?
From string theory. There are, as far as I remember now, there are 2 or 3 axion models. One comes from string theory, one comes from gauge theory. Okay, both are competing.
And the difference is the potential.
Different is, yeah, effectively potential. I mean, on the level of equations of motion, for us, I mean, if you don't want to invent new axion theory, you work with just scalar field.
I have a question for the second part. So you mentioned this idea that that we can have general relativity, and then you can come to this classical thermodynamics, but and then you mentioned this inverse idea that you come from the you say that you have the entropy proportional to the area, and then you go back to infinite. You say that you may try to repeat this with these generalized entropies. Has anybody that?
Yeah.
So what happens?
In principle, you can get also description of the universe. I mean, for example, for inflation, it's perfectly okay, because you have many parameters, so you can achieve it. Then you can reach also, like in modified gravity. That is why I said that there are similarities, even it looks totally different topics. You also may have unification of inflation with dark energy without any big problem. And for example, if you go further, for example, you can give several more generalization, and you can solve the problem of this divergence of Bekenstein-Hawking. So you can propose entropy which does not diverge at 0 temperature.
So you have a sort of correspondence between the parameters of the generalized entropy and the FOR theories, for example.
No, not on the level of entropy, on the level of equations of motion.
Okay.
So from that entropy, you can get equations of motion using thermodynamic approach. Okay, so you will get some modification of gravitational equation, and then you can try to find modified gravity which correspond to this, just to this equation. That's all.
Okay. Any other questions?
Thank you for your talk. I have a question because I'm working on stellar astrophysics, and this point is the first part that you mentioned stellar astrophysics as a way probably to distinguish between the theories. I got the impression that you feel that there is not enough communication between the two communities, stellar astrophysics and theoretical physics. I don't know if that's correct.
Maybe.
Yeah. So I got the impression. I mean, if I was trying to apply a stellar model, I got the impression that the difference between modified gravity theories and general relativity would probably be very small for stellar phenomena.
it's not so. It's I mean, it's small. You are correct. General relativity is good approximate theory to describe, but we have corrections. So, for example, for neutron star, we have correction which may give you some 20-25% difference. You see, you have TOF equations which are different from general relativity. So you have corrections from extra terms, okay? And of course, your mass radius relation will be totally different. I mean, it will coincide with what you have, but in extreme cases, when you have large mass and say a large radius, you will get some difference, which may be 20%. To give you just idea why it happens, it's very simple. You have equation of state with general relativity. Now I have equation of state with alternative gravity. What does alternative gravity? Just effectively addition to equation of state. That's all from gravity. So you should not invent, let's say, some equation of state very realistic with realistic equations of state. You should give, I mean, you should say me better. We have now how many? 15 parameters, realistic equation of state. And still there are problems for some massive neutron stars. Now, with modified gravity, you may think you may improve a little bit.
Thank you. I see there's a message in the chat. Maybe someone.
No, but this is from the very beginning.
That's the first one. Okay. Someone in the Zoom has any question? Otherwise,
Yeah,
our time. Last question.
To make a comment about this question of the stars. And these theories are thought mainly to fix problems like dark energy and matter. And it's a problem of large scale structure, right?
Yeah.
Large scale.
Yeah.
And typically, when some of these theories, they are confronted with other experiments, people say, oh no, but it's a long scale modification. So maybe this theory, you can modify this theory so they don't affect to small scales. But then neutron stars are small scale. They're actually very small scale, right? So then if you take seriously this theory for neutron stars, then also you should probably take seriously for tests that are also at lower scales, like for example binary pulsars, right?
Yeah.
So
You're right. Yeah.
Has this been done?
No, because it's very complicated. High derivative equations.
Yeah.
Okay. So if there's no other question, then thanks, Professor Odintsov again.